Okay, 2.4 equations of kinematics, constant acceleration. Not only are we going to go thoroughly into detail on how these formulas were derived, which is quite simple because we're using constant acceleration here. Also, it's quite genius for Newton who figured this out 300 years before I was even born. Um, Actually, it's probably like 400, 380, 370 years before I was born. It's quite genius. So here's what we're gonna do, and we're gonna explain how each one was derived. I mean, I I don't think I could have figured this out, unfortunately. I mean, I probably could have figured out the derivative, but not this. But anyways, we have a motion in a straight line, constant acceleration. When we say motion in a straight line, it's because if we assume constant acceleration, it's a slope form. Any constant rate of change is going to be a linear line. When the rate of change changes, then we probably have a quadratic, maybe a cubic function. I think linear lines or lines are the only ones with a constant acceleration or rate of change. So, I mean, yeah, that's pretty self-explanatory. So the starting point often is truncated or set to x equals 0 and time equals 0. So that means that regardless, like let's say you're in a classroom and a teacher is right here, and he's writing on the white, or you guys are taking a test or whatever, um, um, a test. If the clock reads 12:15, wait, sorry, it should be the shorthand minute side. 12. Wait, sorry. 12:15. He's not gonna say, okay, let's calculate the time from 12:45, subtract it by 12:15 to get 30 minutes. You have 30 minutes for this test. Instead, he's just gonna start a timer at 12:15, and that timer is gonna read 00, and it's gonna go from there. So that's kind of the logic behind that. I don't know why I had to explain that. That was quite simple to understand. So it's typically truncated or set to x equals 0, which is also displacement. So the position is also set to 0. So if you start on a racetrack halfway, we're not going to say you're halfway around the racetrack. We're going to set that at your starting point or 0. So logic there, really quite easy, simple. Time 0 as well. 5 kinematic variables, x equals displacement, a equals acceleration, which is constant with these kinematic equations. I'm talking a little bit fast. V equals final velocity, or how fast you're traveling at the end. VO equals initial velocity, t equals elapsed time. So let's start with the velocity time relation. And this gives you, V equals VO plus AT, which basically gives you the final velocity. And how does this work? So we have an initial velocity. Let's say a car is moving at 5 meters per second. And then the acceleration squared, which is the rate of change, or the slope, you could say, because this is technically B plus MX formula, or MX plus B, just swapped around. So if we're accelerating at 5 meters divided by seconds squared, that means every 3 seconds, the seconds cancel out, giving us a net change of 15 meters over second velocity change, which gets added to that 5 meters per second, which gives us 20 meters per second as a final velocity. So this initial velocity tells us how much we have originally, and the AT adds, based on the time, how much velocity we are changing, because the velocity changes as a linear line with a constant acceleration as a function of time. So if we plotted velocity and time here, and this was our initial velocity, let's say 5 meters per second, then our velocity looks like this. So depending on the time, you can extrapolate where your final velocity will be. So it's the rate of change plus this. So this tells us how much we're changing per unit of time, and then if we times it by time, we get how much the initial velocity plus how fast this is moving per second times seconds, or how fast we are moving per second and how many seconds we have, and that's just simple math, and that will give you the final velocity. So notice that I'm really trying to explain this here. It really makes sense for me and it clicks in my head, but I know for some people it might not be that easy, so it's a little bit difficult to explain as well. I kind of suck at that. So now we have displacement via average velocity. And this is where it gets a little bit tricky, because first we have to deal with the average velocity formula. So this would be not the average velocity. This would be the final velocity formula. So let's erase that. This is kind of irrelevant at this point. We're going to come back to that when we can't find the time. So this is velocity. And the average velocity formula is VO plus VF over 2. Now you might wonder why. So this is only under the guise of constant acceleration. I don't know why I said guise. So let's make a x and y Cartesian coordinate plane here, or a graph, you could say. And this is going to be time, and this is going to be velocity. So let's say we start here at 0, 0, and we truncate it again. which is kind of what we did or explained right here. And so we started at 0 velocity, and let's just draw this line. And let's come right here, which will be the midpoint. So again, the midpoint, this is the midpoint formula, which is 1 point plus the other point divided by 2. So why does this give us the average velocity? Note that for a line, if directly in the middle, this splits this up into 2 points. So let's assume that this line has a length of c. And if we cut it directly in half, which is what the midpoint formula does, we have c over 2 and c over 2. For every point that is above this line, since they are the same length, there's always another point that is below the line that cancels out. So if we subtract this, because this is technically smaller than the c, if we subtract this point of velocity and this point of velocity, we get this. Simply put, if we took the area here, we can simply move this area right here, giving us a perfect square. Guess what? It has the same velocity as c, or it has the same velocity as the midpoint constantly. So this is the average velocity because this is how fast we are moving. So for this amount of time, which we'll denote as x, until x, we are moving technically, we assume it's a constant rate of velocity, although it's not, but this is how we'll calculate the things. So that means up until x, we kind of assume that it's moving at the midpoint's constant velocity, or we're saying that the car is moving at the midpoint speed, because you can, for every point above here, it cancels out with every point under here, giving us an average of this. So that's the logic behind that. And that means that we can assume that the car is moving at the constant midpoint speed for the entire time, or for an entire half of the line. So very logical, very simple. Now, since we have the average velocity, we can just plug that back into the other formula. Displacement equals velocity times time. And that's the same as VO plus VF divided by 2 times t, which is the displacement as a function of time. In fact, you can probably make this a lot more complicated. VOT plus VFT divided by 2 using algebra. And then you can even make this a little bit more complicated by squaring and then taking square. I don't know what I'm saying, but that's how we got that. Now we get displacement with time, and this one is a little bit more, this one's actually quite genius. So we're going to come back to the original equation, which is x equals VO plus VF over 2 times t. Guess what? Remember here, we have the V equals, wait, I don't know if this is right. Okay, 1 second. Yeah, we solve for VO. And again, we have the final velocity equals VO plus AT. So if we want to solve for, or actually we could just plug this right here back. Or we could solve for VO and it would still give us the same thing. Actually, I'm going to check that right after. So since final velocity is this formula, we could just plug this into this if we already know the initial velocity and the acceleration. So this one kind of assumes that we don't know the final velocity, but it's okay because we have acceleration to do that for us. So all the kinematic equations only give us 4 things. So for velocity time relation, we have the velocity, acceleration, time, and final velocity. Wait, no, we have the velocity, acceleration, time, and the fourth, let me check real quick, and displacement. Well, we don't have displacement here actually. We can calculate it using that. So we have acceleration, velocity, initial velocity, and time. For the second one, we have for this one, we have initial velocity, time, and displacement. We don't have acceleration, but it's okay because the acceleration is a constant slope, which we can calculate using some simple algebra, I guess, or solving for t. Wait, yes, solving for t. For the third one, 2.8. This equation is labeled 2.8 in my book. We have the displacement, because that's what we're calculating, acceleration, initial velocity, and time. We don't have the final velocity. And the last one we have position, acceleration, velocity, initial velocity, and not time. And that's kind of what we're using here. So, I'm sorry if that sounds a little complicated. In other words, you're going to be using each of these equations because one of them is missing one out of the 5 variables. So if you have 4 variables, you can use that to solve the 5th one. Is basically what it's saying here. So again, we just plug that into there. So VOT, or initial velocity times time. Remember, VO is always initial. Even everything with like a 0 subscript probably means at 0 times, so the initial one. So you'll see that in chemistry as well. But we just do VOT because it's the same thing. We're just replacing it. AT divided by 2 times T. Plug that in. It's going to be VOT squared plus... Oh, no, sorry. I mean, yeah, I guess. No, 2 VOT... Oh, no, there's no T here. Sorry. I don't know where I got a T from. It's incorrect. Sorry. Very bad at explaining. So 2 VO divided by 2 plus AT, and then you just apply the T to both sides, T squared, because you're just distributive property. 2 cancels out, so we get VOT plus AT squared over 2 equals displacement. And we'll use this to calculate the displacement if we don't know the final velocity. Quite simple. Now we have the velocity, displacement, no time. And this is where it gets slightly complicated. So do you remember the formula? VF equals VO plus AT. I'm sure this is like the easiest formula ever. A child could solve this. And we'll do VF minus VO divided by A to get time. Guess what? We can replace this into the displacement with time formula. And this is where it gets slightly complicated, so please bear with me. We're going to use some algebra. So I'm good at algebra, but the proofs are always invigorating. So here's what we're going to do. We're going to do VOT plus VOT plus AT squared over 2. So we just plug this into here and to T, so we have VO VF, because I'm just distributing it in my head, minus VO squared over, or not over 8, yeah, over 8, plus A VF minus VO over A, I guess we'll do A squared divided by 2. The A's cancel out here, giving us VO VF minus VO squared over A plus, and we'll use the binomial expansion theorem to do 2 VO VF plus VO squared divided by 2A. We can times this top and bottom by 2A. So we'll do 2 VO VF minus 2 VO squared plus VF squared minus 2 VO VF plus VO squared over 2A. That's a very crooked division sign, but I had to do it because this weird equation was in the way. And using some simple algebra, 2 VOF minus 2 VOF cancels out. VO squared 2 and 2 VO squared, so that leaves negative 1 VO squared. So you have negative VO squared plus VF squared over 2A. And guess what the formula is? The formula is initial velocity plus 2AX. So I think what they did was they times 2A on both sides here. So remember, it's going to be 2AX equals negative VO squared plus VF squared. VF squared equals 2AX plus VO squared. Solved. Quota era demonstratum. I'm just kidding. I guess that's a Latin term for proved. But that is the proof for that one. And basically, this one assumes that you don't know the position or displacement, I believe. Right? Yeah, that one assumes we don't know the displacement. Wait, let me check again, because I feel like we can calculate displacement from that. Let's use my logical book. Also in physics, there's a lot of logics, so those are all the proof formulas. And we'll do a few questions just to make sure that it gets in your head. So that one assumes we don't know displacement, that we're just calculating velocity. This one right here assumes that we don't know the acceleration. Yes, we don't know the acceleration. And we're just going to solve for the position using these 4 terms here. For this one, it assumes that we don't know the final velocity, so we're substituting that in with the acceleration times time squared. But I'm sure you can solve for the final velocity too. It's just slightly more complicated. And this one is just the final velocity squared is equal to initial velocity squared plus 2ax times acceleration times x. If 3 are known, the 4 can be solved. Pretty easy. So let's do some questions here, and I'm just gonna do it myself, not reading off a book. So let me just, I'm gonna read the question off the book. So we have the speedboat has a constant acceleration of 2, and since we're using the metric system, I guess I won't have to clarify that it's meters divided by seconds squared, but I'll do so anyways, just because why not. And if the initial velocity of the boat is 6 meters, if the initial velocity of the boat is 6 meters / seconds, find the boat's displacement after 8 seconds. Also, we have sig figs here, but I'm going to ignore sig figs here just because everyone knows how to do sig figs. If not, I have a video on that. Anyways, so let's see what we're given. We're given acceleration, we're given initial velocity, which is VO, and we're given time, and we're solving for displacement. Guess what formula you can use? We don't have the final velocity, so we can just do the initial velocity, 6 meters times 8, because remember VOT plus AT squared over 2, AT squared, so acceleration is 2, so 2 squared times time divided by 2. So as we use some algebra, we'll do 48 plus 16, and we get 64. So let's see if this is correct using our book. And trying to look here. Oh, sorry, we forgot to square the time. And also, it's AT squared. I accidentally squared the acceleration. So it's 2 because 8 is 2 times t squared, which is 64 divided by 2. 2's cancel out, giving us 48 plus 64. And using some simple algebra, that's 112 meters per meters. So that's the boat's displacement. Let's do another one just to ensure that we can use kinematic formulas. And next we'll go over the application of kinematics. I'm not sure if there's another question in this chapter because I know someone in my class wanted me to do more than one question. I guess I'll do a homework question that I have and kind of explaining how we do that. So give me 1 second just so I can pull up a homework answer or homework question. So we have 1 second. I'm just gonna make sure that you understand this. Also, I'm 1/3 of the way done with AP Physics first semester, I guess. So we'll do 2.4 and 2.5. We'll do 25 odd, and let's see what 25 states. Okay, so 25 says a jogger accelerates from rest to 3 meters / second in 2 seconds. A car accelerates from 38 to 41 meters / second also in 2 seconds. Find the acceleration magnitude only of the jogger and determine acceleration magnitude of the jogger. Find the acceleration of the car. I suck at typing with this keyboard. And we'll do, does the car travel faster than the jogger during the 2 seconds? I'm sure I mean, I guess the logical answer would be no, but then also you gotta remember that a car takes a while to start up. But I'm sure it can go to 0 to 60 in like 2 seconds. So I don't know if this question is as obvious as it seems, or it might be as obvious as it seems. So let's see what we're given. So we're given rest 3 meters in 2 seconds. So that means we have an initial velocity of 0 because we're not moving at all in the beginning, and we have a final velocity of 3 meters per second. So let's find the acceleration. So if it accelerated, acceleration, remember, is Vf minus Vo divided by t, which is just 3 meters slash second divided by 2 seconds. Dimensional analysis, 1.5 meters divided by seconds squared. Simple logic there. So that's the acceleration of the guy. Let's find the acceleration of the car, which is 83. Did it say 83? Oh, it's 38. 38. I was like, that does not seem right. So a car accelerates from 38 to 41 meters, also in 2 seconds. Again, same formula, 41 minus 38 divided by 2. You can apply either way, so that would be 20.5 minus 19, or you can just, subtract that, 3 divided by 2, which is 1.5 meters divided by second squared. So in short, they're moving at the same speed, and no, they're not traveling further, because again, we could just apply the displacement formula. There is no initial velocity. Actually, there is a Oh, I forgot. I mean, the acceleration is the same, but we forgot that the car is moving at an initial speed of 41 meters divided by second. So the car does travel farther than the jogger during the 2 seconds, although they accelerate at the same rate during those 2 seconds. So if we do the displacement formula, we have 41 or 38 times 2 plus at squared, which is 1.5 times 4 divided by 2. So that's going to be 3 plus 76. And that's 79. So it travels 79 meters. And the guy probably, let me just do the math in my head. Or we can just do the at squared formula. So it's going to be 3 meters. Or 1.5 times 2, 4 divided by t, which is 2. So he's going to be traveling 3 meters in that time. So, I mean, or we could have just done the x equals f plus Vo divided by 2 times t. Wait, 1 second. Wait, sorry. Okay, yeah. So this guy traveled 76 meters more. That's the logic behind there, and the acceleration is the same. So that's the beauty behind it. So yeah, I haven't even done this homework, but I guess I'll do it later. And that's 2.4 equation of kinematics. That was a long one, so